What about the charge? I already heard someone float out the charge on our electrons. -1, our protons.
Positive.
Our neutrons.
No charge.
Neutral, no charge. Symbols. E. E for, we are super creative in chemistry. E is for electron. That is not going to be a complete answer, though. What else do we need? We need the negative. What is that negative? It's the charge. Okay, we're adding some information there. Our protons, P, again, super creative, with the positive representing the charge. We're trying to include that information. And the last one, N for neutron and 0. Okay. The line is only included to try and accent it as a 0. When it's so small, if I put a line through it, it disappears. So I won't put a line through it. Okay, now to the harder one, meaning. Okay, or significance. I would argue the easiest one to determine, and I'll go to you guys in just a second, would be protons. Once you define the significance of protons, the rest of them you can start to build off of, because they are all interrelated somehow or another. Okay, so if we can pick up a baseline and say, what extra information do I get with the next particle? So if we start with protons, we can advance from there. What did we decide protons were?
They identify the element.
Okay. They identify the element. If I tell you 2 protons, you can tell me helium. If I tell you 82 protons.
What is that?
Lead.
PB is lead. Okay. So if we know the number of protons, we can identify what element we're looking at. That's really important. Okay. What do the number of electrons tell us? Partially, but I actually want a little bit more. I want to be able to quantify it.
What did he say?
He said reactivity.
Is it the row that they're located in? Or is it the...
It's not even going to be the row, because their row and where they're located on the periodic table is actually due to the number of protons. What do electrons contribute? Charge. What's going to define the charge for the element?
Electrons or protons?
The number of electrons and officially the number of protons. This is why defining the protons first is important. What do the protons define? The element. I now don't need to worry about the number of protons in my charge because the element is now defined by that. What's going to determine how big the charge is? The number of electrons that are counterbalancing that. So my electrons define my charge. Okay. What are the neutrons? You got an idea?
Subatomic particles that have the same mass as a proton but have no charge.
Okay, so what do they contribute then?
They identify isotopes.
They contribute a mass. And we can define the different massed elements as isotopes. So our neutrons help us identify, I usually say mass, but it's probably more appropriate to say isotope. Okay. All of these are interrelated to each other. The neutrons don't define the mass because it's the neutrons and the protons that give me mass. But once I've defined that I'm looking at an element, an individual element, the number of neutrons tells me what the mass is. Kind of make sense?
So you're saying like
I'll step away for that part.
yeah, like it's just so like a simple element like carbon, right? So there's approximately 6 protons, but the weight would change.
Careful. So let's define an element, carbon. And let's not pick carbon because carbon's already on there. Let's pick oxygen. By picking that symbol for oxygen, what can you immediately tell me?
There's 8 protons.
What else can you tell me? How do you know there's 8 electrons?
They have to be like what we were saying, like a sense of magnitude. So big mass.
So up to this point, we always kind of assume that the electrons balance out the protons. Is that always the case? No. I could have just one electron. How do I know that it's not bounced out by a proton? The what? The charge. The charge written where? Where's the charge for an electron written? Look at its symbol. Where's our electron? Where's the charge written? What's the charge for that electron? -1, written in the upper right-hand corner of that symbol. Where's the charge for a proton? Upper right-hand corner. What's the charge for a neutron? Written where? Upper right-hand corner. You will notice that oftentimes for a neutron, you end up seeing it just written as this. Just N. What did we get rid of? Why? It's a 0. Do we care about zeros? Not really, so we can ignore it. What's written in the upper right-hand corner of that oxygen symbol? Upper right-hand corner would be that section right there. What is written right there? Nothing. So what is the charge on that oxygen atom? Nothing. How many electrons does it have to have? Okay. Recognizing where that information is specified allows you to nail down more information. That is why we have 8 protons and electrons, because if we look in that upper right-hand corner, nothing is written there, which means the charge must be 0. For it to be 0, all of those protons must be canceled out. Well, if the proton's positive, it has to be canceled out with what subatomic particle is negative? Electrons. Okay. How do we then decide the number of neutrons? That's a trickier question. We need to get the mass of this atom, okay? And we need to get the atomic mass of this atom. Okay? To figure that out, we'd actually have to weigh it or mass it and all that fun stuff. Let's just say it's 16. If it is 16, how many neutrons do we have? And I see where the slide is. Give me a second. I have 8 neutrons. Why? If I said the mass was 16, what contributes to mass? Neutrons and protons. Not the electrons, it's okay. Our protons contributed 8 to that 16, which means other 8 must come from the neutrons. And we now have the mass of that. Okay? What if we aren't given, of course, now it holds. What if we're just told to look at the periodic table? Okay, well, if we looked at oxygen, it says 16. Go figure, I picked 16. Okay, but let's pick a different element. Chlorine. What is the mass for chlorine? 35.45. How many neutrons in chlorine? Okay, so let's switch it up. Let's pick chlorine. Chlorine has 17 protons plus our number of neutrons. Was it 17? Yeah. Has to equal what? Hearing 34.45? 35. That's one I should know by heart. So how many neutrons do we have? 18.45. Anybody have a problem with that?
Where does the 0.45 come from, the tiny bits of electron mass that there is?
Remember, the electrons were 3 decimal places shifted. There's no way we'd add with just 33 or even 17 electrons. So where is that 0.45 coming from? That makes no sense. The periodic table does not give us the atomic, or sorry, the mole, I gotta use the correct term. I think it's the atomic mass. No, it's not atomic mass. It's the mass number. Thank you. Our protons and neutrons give us our mass number. The periodic table gives us the atomic mass, which is the average of all of the possible isotope combinations. Okay? So using the periodic table, we cannot determine the number of neutrons for an individual element. We need the mass number to figure out those neutrons. Okay? This is a tricky question, which I personally find abhorrent, but it is on the final. I'm glad I recorded that. Okay? It is a common question that shows up on final exams. The difference between a mass number and an atomic mass. The mass number is defined as protons and neutrons. The atomic mass is the average of all of those mass numbers. Okay? Questions about that? Yes?
So if it were to ask them in a certain situation, how many neutrons are there? Would you round up or down, or?
You wouldn't be able to answer the question.
Okay.
That's when you would raise your hand and be like, Mike, there's a typo. And I'd be like, no, there's not. See that little question that says answer not available? Actually, I probably wouldn't point that out. Be like, maybe you should read all of your answer choices very carefully. Okay. Yeah. Okay. Do typos exist? Yes. Regardless of the test, regardless of the instructor, typos exist. One of the options that you have as a student is being an active student and being like, yo, dude, I think there's something wrong with it. Okay? If it comes down to it, I'll look at it, I'll test it. If I see that there's something wrong with it, I'll announce to class and let everybody know. Okay? And that question gets removed. I've done it now a few times over that those typos get fairly infrequent and you don't see that.
Can you repeat this again with the atomic mass and atomic number?
The atomic mass
Is the proton?
is the average mass for the element. Okay, this takes into consideration all of the isotopes. The mass number equals the number of protons plus the number of neutrons. Okay. Very subtly different, but different enough that if someone wanted to ask a definition question, those two common answers pop up. Okay? Does it work? Okay. Other questions? Isotopes. This is where the whole atomic mass comes from. Okay? Hydrogen has two really common isotopes. Okay? They're so common and we so frequently use them that we decided to name them something different than hydrogen. That's where we end up with protium and deuterium. There is also, begins with a T. Not quite. Tritium. What do you think tritium is?
3.
3 for your mass number, which means how many neutrons?
2.
2 neutrons. Right? So when we look to our periodic table, we'll notice that our masses give us fractional values or decimal values. That's because what we're totaling is all possible isotope masses. Some of those isotopes show up in very large populations. Some of them show up in very minimal populations. When we look at hydrogen, for example, its atomic mass is 1.01. How much of hydrogen do you think is deuterium? Ballpark it. A lot? A little?
Quite a bit. Probably.
Let's say it was 50% deuterium. What would the mass be? What would our atomic mass be? 1.5. How did you come up with that? The mass of protium is 1. The mass of deuterium is 2. If I say there's 50% of 1, and I take 50% of 2, and I add those up, what do I get? 1.5. What would the number be? 1.5. What is the number? 1.01. How much deuterium is present? Not 50%. More than 50, less than 50. A lot less than 50%. What is the exact differentiation? It's roughly 99% protium, 1% deuterium. Okay? And if you use those percentages in this calculation, you end up with a mass that comes out to roughly 1.01. Okay? So our isotopes contribute different masses. That's what's shown on our periodic table. Okay? We could go through and look at our protons and neutrons there. I don't really want to do that. Next thing, we could look at our simple versus weighted averages, which I just really quickly showed on the other slide. You guys think you can solve this question, or did you already solve this question? That's the next big question. Did you already see this?
I remember doing it on Thursday.
Okay. So you did it all Thursday, so you can all do it in less than 3 minutes? So we should actually work through it? As a group, or individually first and see how far you can get? Individually. Take a swing at it. If you need some place to start, raise your hand. I'll come to you, talk to you about it, see if we can come up with some way to start this.
The mass and the percent of abundance.
Percent of abundance, what do you mean? Percent of abundance of what?
Of 71 gallon.
Where's the percent of 71?
That was for A, that's what I'm saying. Oh, I'm sorry. 60,
What's the percent?
69, that's what I was sorry.
What's the percent for B?
It's, you take 100%.
If there's only 2 isotopes, when I add the percentages up, what should that equal?
100.
What do I now have the percentage of? I know that B is 100 minus, where is it? 60.11. I think someone was spouting out a number. 39 sounds a little bit better. Okay. So we now have a percent for species B and a percent for species A. Okay. Well, that still doesn't get me the mass for species B. That's, I mean, some more information, but that doesn't help me. What else do I know?
Based on them telling you the element of gallium, you can look at the periodic table and determine its average mass.
I know the element is gallium. And I know because I'm a chemist that I have a periodic table readily available to me, either on the walls of the room that I'm in, or on the front of the exam, or in my cell phone. And you can't use a cell phone on the exam, but you could look at the front of the exam for that periodic table. And what does that periodic table give you? The atomic mass, which is the average mass for the isotopes. So if I take A and I average that with B, what does that then have to equal? My atomic mass. What was the atomic mass according to the table? Really? Oh, yeah, you're totally right. 69.72 AMUs. But this is an average. To take an average, what do you have to do? Divide by the total number of possible things. Well, we've got 2 in this, so we should divide by 2, right? But by dividing by 2, I am necessarily assuming what? Equal abundance of each of those isotopes. I'm assuming both of those are 50%. Is that true? No. So what do we have to do to adjust this? We'll take the percent of A, multiply it by the mass of A. We will add that to the percent of B, and we'll multiply by the mass of B. What do we end up with? 69.72. What numbers do we not know in that formula? The mass of B. Every other number we know, it's now just a question of plug and chug. Solve it out. Okay? It may seem daunting because this is one of the more advanced aspects on solving your weighted averages. Okay? For those of you kind of panicked about this, this is how your grade is calculated. Kind of important. Okay? We're just looking at average grades. We're compiling them and contributing a weight to them. That weight is that percent. How large of a contribution does it make to the overall system? Kind of make sense? I got at least 2 head shakes, yes. And at this point, nobody's shaking their head no. So I'm going to look down and advance. That's the second time you've seen that. Periodic trends, physical properties. Okay. Kind of interested. Did you guys see this question already? Okay. So given the above information, what would be a reasonable density for the potassium atom? In between where? Oh, density. I'm looking in the wrong spot. Somewhere in between those two values. Why'd you pick that? Okay, yes, it gets more dense, but you added an extra statement there. It's not just that it gets more dense, it's that it gets more dense as the periodic table goes. So when we look at the elements provided, where are those elements on our periodic table? They're all directly underneath each other. What do we notice that happens when we look within a row? We notice that the density increases. How much did it increase from first to second? 0.5. How about from, what is that, fourth to fifth? 0.3. How much do we think it's going to increase in between then? 0.3 to 0.4. So we can either subtract 0.3 or 0.4 from 1.53 or add it to 1.97. We'd end up with something that is roughly 1.27. Okay, there we go. Came up with a solid reasoning for that. If we went to a multiple choice test, this is what we could possibly get. Which of those answers is the most sensical? B. What is the actual density for potassium? Those of you looking at the periodic table, it's not up there. They don't tell you that. What's that? No, this is where our periodic table comes into play. It is absolutely impossible to predict. That's what we're using the periodic table to do. We are predicting a value. Our prediction is 1.23. What is the actual value? 0.86. Does that mean our prediction has wrong reasoning? No. Our reasoning is perfectly valid. This is science. What we found is that there's something wrong with that process. We're missing something. So what do we have to do? Go back and change how we made our analysis. Okay? What is the reasoning for the unexpected drop there? Atomic orbitals, okay? Which we will look at in just a little bit. Okay? What I want you to get from the predicting aspect is, do you see a pattern? Match that pattern. Okay? If you go through and memorize the density for every single element, you've wasted your energy. Use the data at hand to predict. That's what you're working towards. Make sense? Okay. So, the trends. There are two trends for atomic radii, and I was told that you know these trends. So, do you have them? Do you have the trends? Yeah? What are they? So we go down a column, our atom gets bigger. Why? This comes back to the two questions that we've got in the middle. What is being measured when we say size? The diameter. And even how big runs into a problem too. Because we could say big is mass. We're not referring to mass when we look at size. We're saying how big. What is the volume that it occupies? What contributes to the volume of our particle or our atom? The number of... Where are the number of protons located? In the nucleus. How small is the nucleus? Itty bitty. Does that contribute to anything to the size? No. What contributes to size? The number of electrons, the things found outside the nucleus. When we go down a column, we go from hydrogen, atom of 1 proton and 1 electron. What happens when we go to lithium? 3 electrons. If we increase the number of electrons, what should happen to the size? It should get bigger. So we go to sodium. 11 electrons, which means bigger. Potassium. Bigger. We're getting closer. Rubidium. Bigger. Cesium. Bigger. Yeah, we're starting to get a little coarse now. So we go down the column, we get bigger. Why? More freaking electrons. The electrons are what make it bigger. What's the other trend?
Rows get bigger from right to left.
So we move right to left. What happens to the atomic size? It gets
Or bigger. Right to left.
smaller. So we move, sorry, right to left. Right to left gets bigger. Sorry, left to right. I don't know how I was doing that. Left to right, it gets smaller. Right to left, it gets bigger. Okay. Explain that one to me. Charge. So I heard something about a stronger charge. What is the charge on a helium? 0. It has no charge. There's 2 protons, 2 electrons. There's no charge. Why is helium smaller than hydrogen if it has more electrons? It does have something to do with the protons. I like where you're going with that. I love it. More protons means they hold tighter and it gets smaller. Hydrogen to lithium? Bigger. What happened to the number of protons? The number of protons increased as we went from hydrogen to lithium, which then means it should get smaller, but it gets bigger. What? How does that make sense? We're missing something. Okay, so let's run it once more. As we go down the column, this one is a straightforward one. What happens as we move down a column? What do we add?
Shells.
We add more electrons, it gets bigger. What happens when we go left to right? It gets smaller. And if you go with the more protons argument, okay, more protons means it gets smaller. What happens to the number of protons as you go down a column? As you move from hydrogen or lithium to sodium, you have the exact same number of protons? No, that gets bigger also. So there's something weird going on with this. Our size does not track perfectly both directions. And the reason why it doesn't track, and we can't explain it right now, has to do with one vital piece of information. The electrons. Where do the electrons exist?
Outside the nucleus.
Right? But they existed outside the nucleus in both cases. If they just existed outside the nucleus, should not more electrons mean bigger? That's not always the case.
Does it have something to do with like there's a greater pole?
It has to do with the exact location of our electrons. Do we know where the exact location of our electrons are yet? No, because at this stage in the game, we don't know that. To figure that out, we actually have to go through and look at light. We go back to chapter 4. This is where, in theory, you talked about light. Someone mentioned amplitude. Don't worry about amplitude. You got wavelength, you got frequency, you've got energy, all that fun stuff. Okay, roughly ballpark, good enough with that? Okay, because that's all I really want you to get out of it. The next big thing I want you to get is the colors of light, because visible light becomes really important to us for the next aspect. Okay? We have what colors in the rainbow? Roy G. Biv, and I'm going to say you are wrong. What colors are in the rainbow? No chartreuse. All the visible colors. Every color is in the rainbow. Why do we call it Roy G. Biv? That orange is the same as that orange? No. So you can't tell me it's just orange. There's gradations of orange. There's gradations of yellow. Why do we call it Roy G. Biv? It's easy. That's it. We established arbitrary marks on our spectrum that has all colors, and we put those arbitrary marks in and said, you are red, you are orange, you are yellow. There is nothing in between. Why did we do that? To make life easier. Okay? Life isn't perfectly easy. It is a complete spectrum that covers all wavelengths and all colors. Okay? Everything is there. When we go through and break it down to red, orange, yellow, the reason we are doing that is because if I asked you which has a higher energy, chartreuse or puce, I don't even know what those two colors are, okay? It makes the question really, really difficult. So we use something like Roy G. Biv because we all recognize red, orange, yellow, green, blue, indigo, and violet. And we can now ask test questions. What would those test questions be? Biggest one is energy. Which one is most energetic? Violet. Okay. How many of you knew that already? How many of you didn't know that? Yeah, how do we remember that? I go outside. What am I concerned about? Heat. Heat? Is heat going to give me cancer? I'm concerned about UV, which is ultraviolet. The thing I'm less concerned about is the heat aspect, which is infrared. Why is ultraviolet more dangerous than infrared? It's higher in energy. Which is closer to ultraviolet? Violet or red? Violet. Purple's higher in energy. Okay? Or sorry, violet is higher in energy. Red, being closer to the infrared end, is less dangerous. Okay? Because it's less energetic. Why do we look at these? Because what ends up happening is that we went through and took some cells, and we took those cells and we pulled everything out of it, and we put just a little bit of a particular element in it, in its gaseous state. Okay? And this is where science gets fun, or potentially really dangerous. Okay? We remove all particles, and then we go through and we try and scare the crap out of whatever we're studying. In this case, we take hydrogen, we put a little bit of hydrogen, and we scare the crap out of it by pumping 10,000 volts through it. What are you going to do when you get 10,000 volts pumped through you? You're going to light up. You're going to freak out and respond to that. So when we did that with hydrogen, what we ended up seeing was a particular color. And when we passed that color through a prism, what does a prism do? Splits the light. When we passed it through that prism, this is what we saw. A line for red, a line at blue-green, and a line at violet. So, well, that's kind of weird. Why do I not just see a bunch of purple? Okay. Why is it not just, say, a whole bunch of purple here, a whole bunch of blue-green there, a whole bunch of red here? Maybe it fades a little bit as it comes in. Why is it coming out as that exact line? Okay. So the reason it's coming out at an exact line because there is only a single energy responsible for emitting that light. I pump in 10,000 volts, I would expect to see a full spectrum of energy. What I end up getting is only little particles, okay, little pieces. What is happening? The element is somehow converting that little or that massive amount of energy into very distinct patterns. Those distinct patterns are where our electrons exist. And it's the electrons jumping between those energy levels that get us the lines. If our electrons can exist anywhere around an individual atom, they're now at tons of different energies. Okay, well, why should they be at different energies? Where would an electron be less reactive? Closer to the nucleus. Why?
Stronger magnetic pole.
Well, why do we care? Are electrons dangerous? No? Anybody stuck your finger in the electrical outlet? What's coming out of the electrical outlet? Electrons. Are electrons dangerous? Yes, they are. They are very high energy particles. When do those high energy particles become less high energy? When they are neutralized. What neutralizes a negatively charged particle? A proton. When I have my electron very close to the proton, what happens? It's neutral, and I have very little energy. If I take that electron and move it really, really, really far away from that center atom, what now happens to the energy? It goes higher. If our electrons can exist anywhere around the atom, what we expect to see is a full spectrum of all the possible ranges of where the electron could exist and where it's moving from. But we don't see that. We see individual lines. A very brilliant man went through and looked at that and said what that means is that the energy for our electrons are quantized. They can only exist at different steps. This is the shells that you guys were starting to quote. Okay? So our electrons are moving at those different orbits. And what happens is when I take, say, my 20,000 volts, and I've got an electron, for hydrogen, where should that electron be first? Where should it start? What do all things tend to do? How many of you are standing in this room? One. Why isn't everybody else standing? Really, you're like, oh, I have no idea why I'm not standing. I wish I could stand anyway. Why is no one standing? It's more energy to stand. It's less energy to sit. Where do we expect the electron to go? To the lowest energy. It's doing the exact same thing you're doing. You're trying to relax. And I'm stressing you out. You're welcome. Okay. So our electron's going to get as close to the nucleus as it can. It's going to get to that innermost orbit. Then what happens if I pump 10,000 volts into you? You're going to jump. Whoosh. With sound effects even. What is that electron now doing at a higher energy? Someone comes in here and immediately grabs and puts you way up high on the ceiling. What are you going to try and do as quickly as possible? Get right back down. Okay? What happens as it comes back down? Can't give off a proton because it's an electron. Photon. It has to release that energy in some fashion. It gets released as a photon, also known as light. The light bands that we are seeing are electrons jumping back down to the ground state. It is that light emission that we see. What happens if we change the energy of that jump? Different light, yes.
So it depends on where the electrons are around the nucleus. That depends what light we see.
Yep.
How come it gives off light? Besides like the energy, what needed? Is that?
Why is it giving off the light?
Yeah.
It was pumped with 10,000 volts.
10,000 volts. Is that just how it expresses the energy?
So there's
Do you get
two
what I'm saying?
different fashions, and you're going to push in a different wavelength.
Okay.
No pun intended there. Ta-da. Never mind. You'll get it later. Okay. What it's going to do is release that energy in some form. The form that we care about happens to be visible light because we see it. That's it. Okay. Are there jumps that give off ultraviolet light? Yep. Why do we not care about those as much? We can't see it. Same for the lower energies. Bohr's theory here tells us that we have these orbitals and these shells. It is those that we are using to place our electrons. That's why we see the distinct atomic fingerprints. Yes?
Group 1 then would be the ones with the highest energy.
We haven't discussed that yet, and we'll get to that. Okay. So this quantized concept, we have a continuous slope. The ball rolls down the slope. Okay. That is continuous because anywhere I place the ball, it immediately rolls. It can occupy any position along that ramp. Quantized means I can only exist at individual steps. I can't place the ball at a half step because there's no half step. Okay. So when we're looking at our atomic orbitals, okay, where our electrons exist, they are quantized. They're individual steps where the electron can exist and only at those steps. Okay. When I then pump 20,000, 10,000, kind of arbitrary, volts into it, I'm moving the ball up to a higher step. That ball then has the opportunity to bounce back down. When the ball is placed up there, does that mean it's necessarily going to roll from that step immediately to the next one? Could it have jumped 2 or 3 steps? Yeah, why not? Okay. Each of those transitions corresponds to a different wavelength. That wavelength can be visible or it could be invisible. But it is those wavelengths that Bohr used to predict his model, and that's why we end up seeing the atomic line spectrum. What happens when we change the element? What have we changed? I moved from hydrogen to helium. What's changed? The amount of electrons. What else changed? The amount of protons. What does that change when we look at our picture? I know our picture is not the greatest here. If I have more protons, what happens to that first energy level? Okay. It should go further away. the protons get, or the electrons get attracted further in, which means your first energy level gets a little bit smaller. Okay? So we change our starting energy levels, which then means we will also change the light or the energy given off when we transition between those steps. So that when we look at, please say it's here, different elements, we don't see the exact same pattern or more lights on top. We notice they change constantly. What we have are the atomic fingerprints, because we're looking at electrons jumping in different elements that are going from different energy orbitals. Okay? To a first approximation, we say all of the energy levels are the same, and we're just saying different jumps within it. Okay? For those of you going, wow, this is really difficult, it is. This is probably one of the most difficult concepts when it comes to chemistry, is dealing with these atomic orbitals and how they function and move. But what we end up with are orbitals. We'll end real quickly with this. We'll start with the lowest energy. What happens as I move the electron further away? Higher energy. Till eventually what happens? Reaches the top. We don't have a top. Energy can keep going up. What happens is I start to pull on, say, your arm. I gradually move that arm further and further away. What eventually happens to your arm? It snaps off. We reach a cap on our atoms. That cap is the electron being ripped away from the atom, moving into the vacuum. Okay. Each of our energy levels is now a place where we can place those electrons. And we can now place more electrons at each of those energy levels to account for our periodic table. What charge is an electron? Negative. What happens when I bring a negative near another negative? They repel. How many electrons can I put in each of these orbitals? One, because put in more, what do they do?
Cancel each other out.
They cancel each other, or they repel away from each other. How many energy levels do I have? 7. That means I can have a total of 7 electrons. How many elements do we have? Slightly more than that. First hint on our simplification, we can actually put 2 electrons in the same orbital because the electrons will occupy different spins. If your mind was blown up before, it's going to be even worse now. Just accept 2 electrons per orbital. What does that help us with? I can now double the electrons. I can now have a whopping 14 elements. Still missing something. That something is what we'll talk about on Thursday.